Hi, everyone. Thank you so much for joining my session, The Importance of Model Fairness and the Interpretability in AI System. I'm Francesca Lazzeri. I'm a senior cloud advocate at Microsoft, where I lead a team of data scientists, AI developers to build an end-to-end solution on Azure. Specifically during this session, we're going to talk about how you, as a data scientist or a developer, can build end-to-end responsible machine learning solutions. We have been writing numerous articles around this important topic. The latest article that you can find is called The Machine Fairness. I put a link there so you can check it out. There are also many resources that we're going to talk about during this session. Some of these resources are open sources, so you can see that we put several different GitHub repos, such as Interpretability GitHub, but also the Fairlearn AI GitHub repo. So you can check it out, all of these links and resources after this session. And again, if you wanted to talk more, feel free to ask me questions. So the agenda for today is going to be divided in three main parts. We have the first part where we're going to talk about what's the responsible AI, what we mean with the responsible artificial intelligence. And then we're going to look at the two main packages. One is called the Interpretability package, and the second one is called the Fairlearn toolkit. As you know, we are in a moment of history where we are all leveraging data in order to making significant decisions that really are going to affect individual lives in different type of domains, such as healthcare, justice, finance, education, marketing, but also HR, employment. So it is very important for us and specifically for our customers to ensure the safe, ethical, and responsible use of artificial intelligence. We know that AI has the potential to drive big changes in the way we do business. And on the other side, like all great technological innovation in the past, is also important that to keep in mind that this type of technological innovation is going to have a very broad impact on society as well. For all these reasons, we think that is important when you build AI solutions and machine learning algorithms to ask yourself the following question. So how can I, as a data scientist and developers, design, build and use AI systems that create a positive impact on individuals and society? Another important question, for example, is how do we best ensure that AI is safe and also reliable? How can we attain the benefit of AI, but also respecting privacy? So these are all open questions that developers and data scientists have. And at Microsoft, we have building different tools that you can use and leverage in your existing solution or to build a new solution in order to assess the fairness level of your machine learning application. Moreover, we also are seeing that many customers are facing the same challenge. There are many different reports here. I'm putting a recent Capgemini report that showed that in 9 out of 10 organizations, we know that they are facing ethical issues in the implementation of AI systems. So this organization cited actually different reasons, including the pressure to quickly implement AI, the failure to consider ethics when implementing AI system, and also the lack of resources dedicated to ethical AI systems. At Microsoft, we build this system that is a sort of a foundation to guide our thinking as a data scientist, and we define 6 ethical principles that AI systems should follow. So as you can see from this slide, the first 4 are fairness, reliability and safety, privacy and security, and finally, we have inclusiveness. So these are really key properties that each AI system should achieve. The second 2 are transparency and accountability. These are somehow underneath all of the other principles and guide how we design, implement, and operationalize AI systems. So let's see what we mean by transparency and how we can implement it. So let's start with transparency. What do we mean actually with transparency? So we mean 2 main things. The first one is that AI system should be explainable, and also that AI system should have algorithms that are accountable, meaning that you can actually understand why they are producing specific results. There are a few cases of machine learning interpretability. We can define them following 2 different categories. As you can see, there is the first one that is a model designer's evaluation. So this is more at the training time. And the second one is end user or providers of a solution to end users. So these are at the inferencing time. This is more the time where they are consuming your AI applications. So there are many different use cases that are important to keep in mind for both categories, like data scientists need to explain the output of a model to stakeholders. Usually these are business users and also clients in order to build trust. Another very important and popular, I would say, use case is when data scientists need tools to verify if a model behavior matches pre-declared objectives. Finally, also data scientists need tools to ensure the fairness of their trained model. Other application and other use cases that are more like from the inferencing time category are when, again, your AI predictions, so the results that you get from your AI application need to be explained at the inferencing time. Some of the most popular cases are in the healthcare and finance industry. So like why a model classified Fabio, like a customer ID, at risk for colon cancer. Another important question from the finance industry that we receive very often is why a specific client, in this case we call her Rosine, was denied a mortgage loan, or why his investment portfolio carries a higher risk. So these are all questions that somehow you have to know how to answer, and specifically you have to know why you got specific results. So that's why at Microsoft, we develop the Interpretability Toolkit. So here is a toolkit that really helps data scientists to interpret and explain their model. And we put together this toolkit in order to explain machine learning models globally, meaning on all the data, or locally on a specific data point, using really state-of-art technology in a very easy to use way. Second, we wanted to incorporate the cutting-edge interpretability solutions that are developed by Microsoft, but also leverage all the open source community solutions. So also this aspect is very important. And finally, we were able to create a common API and also data structure across the integrated libraries and integrate these with Azure ML services. InterpretML is this toolkit that you can find at aka.ms/interpretml toolkit. Really gives you access to the state-of-art interpretability techniques through an open unified API, and also provides you a lot of visualization that you can use in order to understand better why your model is predicting specific results. So with this toolkit, you can understand the models using a wide range of explainers and techniques, using really interactive type of visuals. You can also choose algorithms and experiment with different combination of algorithms. You can also explore, as a data scientist, different model attributes, such as, for example, if you are more interested in the performance or the global and local features, and you can compare again different models, multiple models at the same time. So also this is very nice. In order to find more information, you can again look at this GitHub repo, and also remember that you can run what-if analysis as you manipulate the data and view the impact also of your model. So why did we start this project? In the GitHub repo, you will see that the Interpret community was able to extend Interpret, an open source Python package from Microsoft Research that was used to train interpretable models and helping also to explain black box system. And in just a few minutes, we are going to see also what we mean with the black box system. So this was so the Interpret community was able to extend this Interpret capability with additional interpretability techniques and also utility function to handle also, I would say, real world data set and workflow. So with this package, you can train interpretable glass box models and explain black box system. And also you can use this package to understand your model global behavior or to understand the reason behind each individual prediction. As you can see, Azure Machine Learning is a sort of a wrapper. So we call it Azure ML Interpret. And it's really a wrapper because it helps you save explanation in run history, remote and parallel computing for explanation on Azure ML Compute. So this is an additional capability that Azure ML can offer for you, and also is able to create a scoring explainer for you. And most importantly, if you want to push your model into production, can operationalize these explainers for you. In the GitHub repo, we will also see that there is what we call the Interpret text builds on Interpret. We have added extension to support text models. There are two different types of models that are supported. As you can see, there is what we call the glass box explanations. These are, for example, explainable boosting, linear models, decision tree, rule systems. And we have also a black box explanation like LIME, SHAP, partial dependence, sensitivity analysis. The black box models are challenging in order to understand, for example, deep neural networks. So black box explainers can analyze the relationship between input features and output predictions to interpret models. So as I mentioned in my previous slide, some of the examples can include LIME and SHAP as well. So talking about SHAP, let's take a closer look at it. So SHAP is a game theory approach to explain the output of any machine learning model. So it connects optimal credit allocation with the local explanations using what we call the classic Shapley values from the game theory and also their related extension. So let's see together how we can actually apply SHAP to a real sample machine learning use case. So let's consider a black box that predicts price of a condo or an apartment based on all these features. So as you can see, there is a proximity to a green area, such as a park, and also the fact that the building itself is pet friendly or not. In this case, the feature is negative. So with this in mind, with these features, our model predicts that the average cost of the apartment, the average price of the apartment is 300K. How much has each of these features contributed to the prediction compared to the average prediction? As you can see, We have a different information, such as the house price prediction, that is about 300,000 euro. We have the average house price prediction for all the apartments, and this is about 310 euros. So the delta here is negative, is a minus 10,000 K. So these are the Shipley values. So as you can see, we have different features. So let's start with the parks. So how the parks contributed to these result. So we have plus 10K. Then we have the fact that the cats were banned, also contributed in a negative way, 50K. So the fact that the building itself is not pet friendly. Also, the size of the apartment is a very important feature in this case. And we see that it contributed actually to 10K. And then we also see that there is a final feature that is the fact that the apartment is at the second floor. It had a zero neat contribution. So these final attributes, this final feature actually was not really impacting our model results. So how did calculate, or how did actually Sharply calculate all these values? So we will take features of interest, for example, cat's ban, and we remove it from the feature set. Second, we take the remaining features and we generate all possible collision. And finally, we add and remove your feature of interest to each of these collision, and we calculate the difference that it makes. So this is really how Sharp works. So this is really the logic that is behind Sharp. Of course, there are some pros and cons that it's important to keep in mind when you decide to use a Sharp. For example, Sharp is great because it's based on a solid theory of and also distributes the effects in a very fair way. However, on the other side, it produces also contrastive explanation, what I call like explanation that sometimes even instead of comparing a prediction to an average prediction of the entire data set, you could compare it to a subset or even to a single data point. But in terms of what are the cons for Sharp, computation time is it's possible that, for example, you can use like a 2K, more or less, possible collision of the feature values, 4K features. Sometimes it's difficult to understand it, so it can be misinterpreted. And finally, the inclusion of unrealistic data instances when the features are correlated is also very possible. So it's a risk that you should keep in mind when you decided to use Sharp. So as I said, there are also different models that you can use. There are different also interpretability approaches based on how you want to use these different models. So in terms of glass box models, these are models that are interpretable due to their structure. Examples are explainable boosting machines, linear models, and also decision trees. Glass box models produce lossless explanations and are editable by domain expert, which is something very, very nice to have when you want, again, to use and leverage these glass box type of models. So in terms of GLM, so this is a generalized linear model. As you can see, this is a flexible generalization of an ordinary linear regression that allows for responsive variables that have error distribution models other than normal distributions. So as you can see, the main characteristic of generalized linear models is that are the current standard for interpretable models, and also that they learn an additive relationship between data and response. Another example is the explainable boosting machine. So here you can call them also EBM. This is a sort of interpretable model that has been developed by Microsoft Research. It is a very interesting model because it uses modern machine learning techniques like debugging, gradient boosting, and also automatic interaction detection to improve traditional generalized additive models. This is why actually the explainable boosting machine are very accurate and they are considered like a very good techniques, like for example the random forest and also gradient boosted trees. So in this second part of the presentation, we're going actually to focus on fairness. We are going to see what are the different fairness principles, which aims to tackle the question on how we can ensure that AI systems treat everyone in a fair ways. Fairness has a main goal to provide more positive outcomes and avoiding harmful outcomes of AI systems for different groups of people. There are different types of harm, as you can see from these slides. Broadly speaking, I would say that we developed these different types of harms based on the taxonomy that Microsoft Research created. And there are 5 different types of harm that you can see in a machine learning system. And while I have the definition of all of them in these slides, for the scope of this project, we'd actually just focus on the first 2 of them that are allocation, as you can see. This is the harms that can occur when AI system extends, or I would say withhold opportunities, resources, or information to specific groups of people. And then we have the other one, which is quality of service. This is whether a system works as well for one person as it does for another person. So the example of the face recognition from many different applications is probably one of the most important example of the quality of the service. For this fairness part, Microsoft developed a new toolkit that is called Fair Learn. This is a new approach to measuring and mitigating unfairness in systems that make predictions, serve users, or make decisions about allocating resources, opportunities, or informations. There are many ways that AI systems can behave unfairly. For example, AI can impact the quality of service, which is, again, whether a system works as well for one person as it does for another. And also AI can also impact allocation, which is, again, the harm that occur when AI system extends or withhold opportunities, resources, or information to specific groups of peoples. So as you can see in the toolkit, that again you can find more at aka.ms/fairlearnai. In this toolkit, there are different type of focuses and different type of, I would say, capabilities. So the main goal of this toolkit is to empower developers of artificial intelligence systems to assess their system fairness and also mitigate any observed fairness issues. Most importantly, it helps users identify and mitigate unfairness in their machine learning models with a focus on group fairness. So now let's jump actually on a demo. I want to show you how you can use the interpretability toolkit. So in this demo, we're going to see how you can use the interpretability toolkit for tabular data in Azure Databricks. As you can see, we are going to see what's the toolkit that you can use and download for the explanation results from the explanation experiment, and also visualize the feature importance. Implementing advanced analytics solution in every organization and for each of our customers is, I would say, a four different step process. So you first need to ingest the data from a different variety of data sources, including batch and streaming data. And as you can see, there are different options here, as this architecture shows us. And then the most important part is that, of course, you need to take in and store disparate data that's being ingested, regardless of the data volumes, variety, and velocity. Here you can do it, of course, with different type of products. When you get into the prep and train stage, you can use, again, Azure Databricks just to train and deploy your model. As you can see, in Databricks, we have an option that is called Runtime now that includes a variety of popular libraries. The libraries are updated with each release to include like new features. So the Azure Databricks has designated a subset of the supported library as a sort of top tier libraries. For these libraries, Azure Databricks provides a faster update cadence, updating to the latest package releases with each runtime release. So this is very good for data scientists as well. In terms of dataset, so we are going to use these breast cancer Wisconsin dataset that is a public dataset. Here you can see that there are different attributes that we're going to use for this demo. And not only in terms of ID number and diagnosis, which are probably the most important attributes, but also there are real value features that are computed for each cells nucleus that we are going to analyze for this specific demo. So first of all, you need to, next. First of all, you need to install Azure ML Interpret and Azure ML Contrib Interpret packages. Next, you need to train a sample model in a local Jupyter notebook. As you can see, you can again use the breast cancer data set, and then you can split the data into train and test. Third, you can call the explainer locally. Here you need to initialize an explainer object, pass your model, and then do some training data to the explainer constructor. In order to make explanation and visualization more informative, you can also choose to pass in feature names and output class that are names in output class names. For example, if you're doing a classification. This code that you see in these slides actually show you how you can instantiate an explainer object with different types of example. Here specifically you have the tabular explainer and the PFI explainer in a local environment. Then, if you want to explain the entire model behavior, you can call what we call the global explanation. So this is going actually to give you a sort of a visualization that you can, again, leverage to understand and interpret better your models. So some of these visualization, again, are produced from your Python code, just using these packages. And I want just to show you some of the visualization that this package can create for you. As you can see, there is here an overall view of the train model along with its predictions and explanations. So we have the data exploration. This displays an overview of the data set along with the prediction values. Then we have the global importance. These aggregates features importance values of individual data points to show the model's overall top K. These are, of course, configurable type of K, so you can change that number. These are important features, and also helps understanding of underlying models' overall behavior. Then we have the exploration. So this demonstrates how a feature affects a change in the model prediction values, or also the probability of the prediction values. It's a very good visualization if you want to show the impact of a feature interaction. Finally, we have the summary importance. So this uses different individual features importance values across all the data points to show the distribution of each feature's impact on the prediction value. By using this diagram, you can investigate, for example, in what direction the feature values affects the prediction value. Another way to understand better what your model is actually doing is by using the local explanation. You can see that here you can get the individual feature importance values of different data points by calling explanation for an individual instance or for a different group of instances. Here we have a different type of visualization that are created. First of all, we have the local importance. This shows the top K important features for an individual prediction, and it's very helpful when a data scientist wants to illustrate the local behavior of the underlying model on a specific data point. Then we have the perturbation exploration. It's a sort of a what-if analysis. As you can see, this visualization allows changes to feature values of the selected data point and observe resulting changes to prediction value. Finally, another important visualization that I want to share with you is called the individual conditional expectation. This visualization allows a feature value changes from a minimum value to a maximum value. So it's very helpful when a data scientist needs to illustrate how the data points prediction changes when a feature changes. Again, this was just an overview of what the interpretability toolkit can do for you and how you can leverage that on your solutions. I want also to share additional contacts of the product team who work on this toolkit. As you can see, you can find their names and their emails there in case you want also to follow up offline with the product team, again, who put together all these toolkits that I presented today. Again, this is one of the articles that you can use to learn more and also to find some of the resources that have been used today during this session. And in terms of resources, I just want to share those with you one more time. These are all the packages and the GitHub repo that have been used during this session. And you can also find me on Twitter, GitHub, and Medium. Thank you very much.